For the first time in history, humanity may have detected a chemical clue that hints, however cautiously, at the possibility of life on another world. Not a radio transmission. Not an alien spacecraft. Not towering cities illuminated beneath distant skies. Instead, the clue arrived as something far more subtle. A faint molecular signature hidden within the atmosphere of a planet orbiting a star 120 light-years away. That single observation ignited one of the most intense scientific debates in recent memory. When researchers announced their findings, excitement spread rapidly across the world. Some astronomers believed the James Webb Space Telescope had uncovered one of the strongest potential biosignatures ever observed beyond our solar system. Others urged caution, arguing that the evidence remained incomplete and that alternative explanations had not been ruled out. Months later, the discussion had only become more complicated. The greatest mystery was no longer whether Webb had collected extraordinary data. It was whether humanity could confidently interpret what that data actually meant. At the center of the debate is a planet known as K218b. This world bears little resemblance to Earth. It is roughly 8 times more massive than our planet and about 2.5 times larger in diameter. Rather than orbiting a sun-like star, K218b circles a small, cool red dwarf located in the constellation Leo, completing one orbit every 33 days. Most importantly, the planet lies within its star's habitable zone, the region where temperatures may allow liquid water to exist under suitable atmospheric conditions. That alone made K218b one of the most interesting exoplanets ever discovered. But the real story lies in its atmosphere. Because the planet cannot be photographed directly, astronomers study it using a technique called transit spectroscopy. Whenever K218b passes in front of its star from Earth's perspective, a tiny portion of the starlight passes through the planet's atmosphere before reaching the James Webb Space Telescope. Different molecules absorb different wavelengths of light. Those tiny missing wavelengths act like fingerprints, allowing scientists to estimate which gases are present, even though the planet itself appears as nothing more than a distant point of light. In 2019, observations from the Hubble Space Telescope revealed evidence for water vapor, immediately placing K218b among the most promising candidates for atmospheric study. When James Webb turned its far more powerful instruments toward the same world, researchers expected clearer answers. Instead, they discovered a far deeper mystery. The telescope detected strong evidence for carbon dioxide and methane, while ammonia appeared to be absent or significantly depleted. That combination attracted attention because it matched theoretical predictions for a proposed class of planets known as Hycean worlds. The term combines the words hydrogen and ocean. According to this hypothesis, Hycean planets possess thick hydrogen-rich atmospheres covering vast global oceans beneath. Unlike Earth, such worlds could experience very different temperatures, pressures, and atmospheric chemistry while still potentially supporting environments where life might exist. K218b seemed to fit many of those expectations. Then came the observation that transformed scientific curiosity into worldwide headlines. Researchers identified a tentative signal that could correspond to dimethyl sulfide commonly abbreviated as DMS. On Earth, this sulfur-containing molecule is produced primarily by microscopic marine organisms, especially phytoplankton. Because biological activity is by far its dominant source on our planet, astrobiologists have long regarded DMS as one of several promising candidate biosignature gases. The initial indication was weak. No one claimed that alien life had been discovered. Instead, scientists described the result as an intriguing possibility that demanded additional observations. When Webb later observed K218b using another instrument covering different infrared wavelengths, the possible signal appeared stronger. Researchers suggested that the data might contain signatures of dimethyl sulfide, dimethyl disulfide, or perhaps a combination of both molecules. Statistically, the confidence level reached approximately 3 sigma. Within science, that represents evidence worthy of careful attention, but it falls well short of the level required for an extraordinary discovery. Nevertheless, the announcement captured global attention. For a brief moment, it seemed humanity might be approaching an answer to one of its oldest questions. Then the scientific process began. Independent research groups analyzed exactly the same Webb observations using different calibration methods, atmospheric models, and statistical techniques. The results did not all agree. Some teams concluded that the evidence for DMS remained too uncertain. Others suggested that different atmospheric molecules could potentially reproduce similar spectral features. Still others questioned parts of the broader atmospheric interpretation, arguing that several aspects of K218b remain insufficiently constrained. One particularly difficult challenge involves what astronomers call *correlated noise*, sometimes referred to as red noise.